Okay, so what kind of graph is this bad boy? Tan. Okay, it looks real crazy. So we know it's something to do with tan x. We know that our normal period for our tan graph is 180. 180. So we're going to look to see here what is our period here. Or, as I've said here, it may be easier to determine how many cycles there are within our usual 180. So if we started looking at this 180 period, we've got a little portion, we've got a whole portion, and a little baby bit. So how many cycles have we done? So that means our value here is 2. So it will be y equals tan 2x. Okay?
How can you count the other line?
You good? Yeah. This one, is it sine or cos? Cos. Again, how many, so you can either look at what the period is or how many cycles it's done within 360. How many cycles has this one done within 360? Be careful when you get the blue one. Yeah. What's up? Alright, so we can see that it's gone through half a period, yes? Yeah. Or in other words, our full period would have taken us all the way to 720, yes? So our period was 720, or we can see that it's only done half a cycle within our normal 360. So this one would actually be y equals cos of x over 2, or cos half x. Okay. So, this bad boy, these are those ones. So, you've got inside the bracket, you've got your adding or subtracting something. This one's going to shift it horizontally. So it's not actually changing the amplitude or the period or the central line. It's just moving it left or right. Okay. Now, the value that we're adding or subtracting will be a number of degrees. All right. As I said here, choose a familiar point of the graph and see how that's shifted. Another note is there will be options when it comes to sine or cos, because the whole nature of the graphs is that they are translations of each other. So if we actually go back to the originals, if we had the cos and the sine graph on the same, no, I've done that. If I was to draw the cos graph, okay, so there's my cos graph on the same as my sine. I can see that actually this graph here is just a shift to the right. Equally, this graph here is a shift to the left of that one. And it's a shift of 90 degrees. So we could say that this graph here, the blue one, compared to this one, could be sine, because this is a sine, of x minus, no, plus 90, because it shifted left 90 units. Are you with me? And so sine of x plus 90 is the same as cos of x. Yeah? Like that. So the sine of x plus 90 is the same as cos x. Yeah? Because it is the shift of it. So the blue one is cos x, yes?
Okay.
But I can describe it using sine, because I know that this blue one is this black graph shifted left by 90 units, by 90 degrees. Yeah? But it also means that if you're trying to describe something, generally they will start the question off, if it has shifted, they will say this is cos or sine. So they will tell you which one it is. So you're not, well, there could be two options here. Okay? And I mean, obviously you can describe any of them. You can say minus whatever, however much it shifted. Okay? So we've actually just talked about this. So, oh, John, look at that. Where did I get that? All right. All right, so it's going to shift it, and as we talked about before, if it's a plus value here, it's actually going to shift it to the left by that number of units, and if this was negative, it would shift it right. Okay, remember it's always going to the opposite direction. So here, if as I said, we need to identify if it's a sine or cos. The black one here was a which one? Black one, sine. Okay, so we're going to base this one on the sine x. Oh, Miss Harrison. Well, I haven't really shown you where the values are.
Yeah.
That's rubbish. Okay, shush now, and we can use this one. So, what point was that normally? 360. Now, where is it going through now? 300. So that means that this movement is how many degrees? Okay, that's all good. Yeah. So secretly we've gone left 60 degrees, yes? So from the black to the blue, we've gone left 60 degrees. So if we're going left, we know it's going to be a plus value. So this must be a translation of 60 degrees left. And so the equation would be y equals sine of x plus 60. Okay. All right, so this here is our general sine function. So we've talked about the fact that the value of front would affect the amplitude. This value b affects the periods. This c affects horizontal translation, and this d would affect vertical translation. So going back to should you choose to do this, to model some data that looks like it's trigonometric, you would identify all of these are called parameters. So the a, the b, the c, and the d, they're known as parameters. And you will identify what those values are by looking at the graph that you have. Okay. Rather than central line, they talk about the principal axis. Okay, so they talk about the principal axis, that's the central line. So that means the same as what I was talking about, that central line would start at 0 normally, and then obviously whatever value is we have here, that's going to tell you what the central line is. The amplitude is the size of A. Okay. Now, if your graph did this, okay, that's very similar to the sine graph, isn't it?
Mm-hmm.
But what's different about it?
It doesn't go like it has to be wide.
Well, it does. It just makes a map of this. So what happens to it? What might have happened to it? Reflected, yes? Can we all see that that's a reflection of the normal sine graph?
Yeah.
Yes? So our normal sine graph would have done that. Yeah? No, so this is an S through the thingy.
Oh.
Okay?
Yep.
So, because the red one is a reflection in it, what does it tell us about the value in front of here?
It's positive.
Negative. It would be negative. So the red one would have a negative value here. Yes? So we haven't talked about negatives, but that situation would happen here. You'll see that?
Yeah.
So if your data happens to go down first and then up, then it's going to have a negative value here. Alright? Cosine, same situation. Tangent, same situation. Oh yeah, I forgot about this one. Features of them. Lovely. So, summary of information for you. Excellent. And again, what's happened to it? So these are how that they are affected. And now, this here to pi, they are radians, okay? So because we haven't discussed radians yet, you would imagine that said 360, and this one you would imagine says 180. Okay, but later on we'll be happy with it. Got 5 minutes. I may as well just go through this, shall I?
Yeah.
Seeing as we've not really got anything else. And so modelling using the sine function. So below is a table which shows the mean monthly maximum temperatures for a city of Greece. Okay, so we've got January, February, March, April, May, there. Using a sine function of the form T is a... Now, we use this here because this is going to be a model for it, so it's definitely not going to be exact. So this is indicating that it's approximately going to be looking like this. Find good estimates of the constants A, B, and C, and D without using technology. Now, what they've said is that you're going to use January to be represented by the number 1, because obviously we can't plot a sine graph with Jan, Feb, March, April. We need numbers. Okay? So, what would we do? We can see our values are all positive, so we actually don't need to go into the negatives. So we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? Yeah, I do. Do you want to just watch it and then you can do it?
Yeah.
Alright, so here's my 1 to 12. My data's going up here. Oh, here we go. Up 26. Where's 27? Oh, God. Darn it. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. God, that's rubbish. 3's a horrible number. No. 5's too little, surely. How about 4?
No, because 5 is 25.
4, 8, 12, 16, 20, 24, 28. That's a bit better. Obviously, when you're doing yours, you do beautifully. Alright, so we're going to plot these as coordinates. So we would plot 1 and 15, 2 and 14, 3 and 15, 4 and 18. It's a rubbish scale comparison. Yeah. Right, I'm going to have to one of these bad boys, you know? Yeah. At the heartbeat. Let's start at 10. 12, 14, 16, oh, far out. Perhaps I shouldn't be recording. Okay, so now we've drawn our data. We can see roughly it goes in the shape of a sine graph. Yes? We see that?
Yeah. Yes.
Oh, they told us it's going to be a sine.
Well, why don't go through the
Okay, so this is the situation. So remember, so this is what you have to follow what they've asked you to do. So you might have naturally gone for a cos here, but they told us we're going for sine. Okay. So what we need to do is to establish what these values here would be. Now we know that this number here tells us about the amplitude. Yes. Mm-hmm. So you would find your maximum point. So our maximum point was at 27. Mm-hmm. So we would find A by doing 27 plus our minimum point, which was at 14. 14, and we would divide that by 2. Okay, so 27 plus 14 is 41. Over 2 gives us 20.5. So we found the value of A to be 20.5. Now, next thing I would probably personally do is find my central line, so I'd probably find D next, because I know that's halfway between those 2 points. So rather than what have I done wrong there? I was supposed to take this away, Nana. Because if this is the top and this is the bottom, we subtract them sides of each other, don't we? And divide by 2. So 13 divided by 2 is 6.5. Yes, that's more like it, Donna. The D is found by 27 plus 14 divided by 2. So we know our central line is at 20.5. That looks right. And we know that this measurement here is 6.5. You with me now?
Yes.
Down.